The substitution rule. This is intended to be a review for Calculus 2 students. The substitution rule states that if u equals g of x is a differentiable function whose range is on an interval I and f is continuous on I, then the integral of f of g of x times g prime of x can be written as f of u times du. The fundamental concept is that if you are trying to integrate a complicated function, we might be able to simplify it by letting u be equal to g of x, where g of x is the inside function of a composition of two functions. In doing this, du can be written as g prime of x times dx. And if we have the g prime of x readily available, we can make a direct substitution, u taking the place of g of x, and du taking the place of g prime of x times dx, and that gives us a simple integral. So the thing to remember about the substitution rule is that it is a rule that is intended to take a complicated integral and turn it into a simple one. Let's take a look at our first example. Here we have the integral of 5 minus 3x to the 10th power. One way to do this is you could multiply 5 minus 3x by itself 10 times. And you actually could do this, but it would take a lot of work and a lot of time to do that. So instead, what I'm going to do is let u be the function 5 minus 3x. And if that's the case, then du would be negative 3 times dx. Now, when we do this, 5 minus 3x to the 10th power is going to become u to the 10th power. But then we need to make sure we have the du in our integral. Now, you'll notice that we do not have the negative 3 that is multiplied to the dx. So there's a couple of different ways to handle this. Let me show you the first way. What I can do here is I can rewrite this integral as the integral of 5 minus 3x to the 10th power, and then I'm going to multiply by negative 3 dx. But I can't simply just put the negative 3 in there, because when I do that, I've changed the problem. So on the outside of the integral, I'm going to put a negative 1/3, with the understanding that if we were to multiply these together, they would cancel out, and it would give us the integral that we started with. So this integral now becomes negative 1/3 integral 5 minus 3x to the 10th power can now be written as u to the 10th power, and negative 3 times dx can be replaced with du. And now we can take the antiderivative with relative ease. We know the antiderivative of u to the 10th, du, is simply u to the 11 divided by 11. And so now we have negative 1 over 33 times u to the 11, but u is 5 minus 3x. So I'm going to substitute that back in, and then make sure you add your arbitrary constant. And it is true that you could write this answer slightly different. So we could also express the answer as a single fraction like so. And there really is no better answer here. Both of these are just fine. Let me show you another way to deal with the du part of this integral. Another way to do this problem is to go back to your substitution here and solve for dx. So if du is equal to negative 3 times dx, I can divide both sides by negative 3, and that would cancel the negative 3 here, and we would get dx is equal to du divided by negative 3. And now what we can do is just make direct substitutions into our integral. So 5 minus 3x to the 10th power becomes u to the 10th power. And then dx becomes du divided by negative 3. Now, some people prefer to do it this way, and there's nothing wrong with doing it this way or the original way that I showed you. But if you do it this way, you still need to factor the negative 3 out of the integral here. And please pay attention to the fact that this negative 3 is in the denominator. So when you factor it out, it will be in the denominator of the fraction. So we need to think of that as negative 1/3. And then from here, it is exactly the same as what we did just a few moments ago. And then don't forget to put your arbitrary constant. In the next example, we have a fraction, and there is a general rule when dealing with fractions, and this rule is not always true, but it is often true, and that is that you will often want to let u be equal to the denominator of the fraction, or something in the denominator. So when I get a problem like this, I'm going to try this first. I'm going to let u be equal to z to the 3rd power plus 1, and let's see what happens if I do that. Du, of course, is 3z squared times dz. And you'll notice that we have z squared times dz right there. And that's really good. That's what we need. Okay, but we do not have the 3 there. So again, one way to deal with this is we could simply put the 3 in. And if you do that, put a 1/3 on the outside. And the reason you can do this is because 1/3 times 3 would cancel, and it would give you the integral that you started with. So now if I make our substitution, we have 1/3 integral. Remember, 3z squared dz is all du now, and that goes on top. And then in the bottom, you just have u, because z cubed plus 1 is u. And this is exactly why you do it this way, because we know that the antiderivative of 1 over u du is the natural log of the absolute value of u. And then don't forget to have your 1/3 in front. And then lastly, you're going to plug in the original expression back in for u. So u is equal to z cubed plus 1. And so here is our final answer. And just one comment to make about this. Sometimes students will get a little bit confused when they see something like du over u. So let's remember that du over u is the same as 1 times du over u, and that can be written as 1 over u times du. And sometimes that is helpful for seeing that this is the natural log, because of course 1 over u is the derivative of the natural log function. Now, if you don't need to do this, I would say just take it straight from here to the next step, but sometimes this is helpful. In the next example, we have another fraction, and I want to show you that if you let u be equal to the denominator of the fraction, x squared, then du would be 2x dx. And I really hope that it's somewhat obvious to you that this is not the way to do the substitution. If I rewrite my integral, what we have here is the sine of 1 over x dx over x squared. And there's nothing here that helps us, right? The u is down here. And then what about 1 over x? What is that? So this is not the correct substitution. So in the previous example, I mentioned that if you have a fraction, you will often, in fact, most of the time, you will let u be equal to the denominator. But I wanted to show you right away that that is not always going to be the case. So for this particular problem, I'm actually going to try letting u be equal to the inside of the sine function, which is the function 1 over x. Now, du is the derivative of 1 over x, which is negative 1 over x squared, times dx. And let's remember that 1 over x can be thought of as x to the negative 1, and when you do your derivative, you use the power rule for differentiation, okay? So that is how I got this negative 1 over x squared. The derivative of 1 over x is a derivative that you should memorize because it comes up all the time. But now I want you to see that you essentially have this in your integral, right? This is basically 1 over x squared here. You just don't have the negative. So let's rewrite this as the integral of the sine of 1 over x, and then dx off to the side, x squared in the bottom, and then I'm going to put a negative 1 here, and I'll put a negative 1 on the outside. And that's because negative 1 times negative 1 would cancel, giving us the original problem that we had. Now what I want to point out to you is this is negative 1 over x squared times dx. And that's all this right here. And so that can be replaced with du. And then, of course, 1 over x is this thing here. So when we make our substitutions here, don't forget you have a negative on the outside, integral, and you're going to have the sine of u and then du. And this is certainly an integral that we know how to do. We have negative, and then the integral of sine of u is negative cosine of u. And negative cosine, of course, is just cosine. And then we are going to put our u back in as an x function. In this case, that is 1 over x, and then plus c. Another fraction in this one. And so I'm going to go ahead and do what I told you to do. I'm going to let u be equal to the denominator. I'm always going to try that first to see what happens. If I do that, then du is going to be 4 times dx. Now, notice that we do not have 4 dx, but that's okay. We can multiply by 4 here, as long as we remember to multiply by 1/4 on the outside. And this becomes 1/4 integral. 4 dx is replaced with du. And 4x plus 7 here is replaced with u. And so this becomes 1/4 natural log absolute value of u. And when we resubstitute u equals 4x plus 7 back into the problem here, we end up getting our final answer, 1/4 natural log absolute value of 4x plus 7 plus c. This next one is a little bit interesting just because of the type of expression that we have inside of our sine function here. So there's really nothing else going on in this problem except that you have this pi t over 3 in your sine function. So first, let me just rewrite this as sine, and then I'm going to put that fraction vertically, pi t over 3, like this, dt. And I'm going to let u be equal to the inside part of the sine function, pi t over 3. And what I need is du. Now, this can be a little bit tricky, but let's remember that pi t over 3 is the same as pi over 3 times t. And we know that the derivative of a number multiplied by a variable is just the number. So it's pi over 3 and then dt. So when you go back to your problem here, you'll notice that we have the dt, of course, but we do not have the pi over 3 next to the dt. And the one that's inside the sine function doesn't count. So I'm going to come down here and rewrite this with a little more space. Okay, and then you'll know that I need to have this pi over 3 in front of my dt. So let me go ahead and put it in there, pi over 3. And then I have to compensate for that on the outside of the integral by putting the reciprocal of pi over 3, which is 3 over pi. Now, the whole point is, if we were to multiply these together, the pi's and the 3's would cancel out, and it would give you the integral that we started with. But the nice thing is, we now have our u right here, and we have our du right there. And so this becomes 3 over pi integral sine of u du. And this is going to be 3 over pi. The antiderivative of sine of u is negative cosine of u. We'll factor the negative out in front of the 3 over pi. We have cosine, and then u is pi t over 3 plus c. So this is pretty much the same as previous problems. It's just that the expression we had here is a little bit unfamiliar. And when you have that, just break it down into its fundamental meaning. Okay, in our next example, we have the integral of x squared times the square root of 2 plus x. When you have a radical involved in your integral, you will almost always let u be equal to the inside of the radical. So I'm going to try that first. Now if I do that, du is simply going to be the derivative of x, which is 1 dx. So that's good news because we have a dx right here, and that can be replaced with du, and 2 plus x can be replaced with u. So the question is, what do we do with the extra x squared we have there? Well, what you do is you go back to your original substitution here, and you solve for x. And you could say x is equal to u minus 2 by simply subtracting 2 from both sides. Now, let's go back to the integral. X squared, well, x squared would be the same as u minus 2 squared. So I can put in u minus 2 squared to replace x squared. The square root of 2 plus x becomes the square root of u, because u is 2 plus x, and then dx simply becomes du. So remember, when you're doing substitution, everything that used to be an x has to be translated into the new variable, in this case u. Now from here, you just need to remember fundamental principles of integration. So u minus 2 to the second power, I can multiply that out. And then we're going to take the square root of u and we're going to distribute it to all of these. Now when I do that step, we're going to get u squared minus 4u plus 4 times u to the 1/2 du. So remember, when you multiply by a radical, you want to change it to a half power. That way, when you multiply these together here, you can add the exponents. And so this becomes u to the 2 plus 1/2, which is 5/2, minus 4 times u to the 1/2 is u to the 3 over 2, and then plus 4 u to the 1 over 2 du. Now from here we can use the power rule. So we're going to integrate this by adding 1 to that power and then dividing by that number. Now if you can do this in your head, that's perfectly fine. Go ahead and do that, but I do recommend that you write down these steps, especially in the beginning when you're reviewing some of this stuff. So I'm doing the same thing to the next two terms. And now I'm just going to do the math here. We get u to the 7 over 2 divided by 7 over 2 minus 4u to the 5 over 2 divided by 5 over 2 plus 4u to the 3 over 2 divided by 3 over 2. Now when you divide by a fraction, you're going to invert and multiply. So this 5/2 here is going to become 2/5 times, don't forget you had a 4 here. And then same thing on the last one. And then we're going to plug our u back in. So let's remember that u, where is it at? Here it is. U was 2 plus x. Now, if u is 2 plus x, you can also write that as x plus 2. To be honest with you, I prefer to write it as x plus 2. So this is 2/7 x plus 2 to the 7/2 minus, let's multiply these. We get 8 over 5 x plus 2 to the 5/2 plus 8 over 3 x plus 2 to the 3/2 plus c. So that is a pretty impressive antiderivative there. In the next example, we have yet another radical. So I'll start it the same way. I'm going to let u be equal to x squared plus 1. du, of course, is 2x times dx. Now, if you look at this, we have the dx, but I don't see the 2x. But we do have this x cubed here. So let's remember that x cubed can be written as x squared times x. And so if I break that apart here, we have x squared times x times the square root of x squared plus 1 times dx. And if you look carefully here, we do have an x multiplied by a dx, and we need that for our du. So if you want, what you can do is reorder things so that it's a little bit easier to see. So I can put this x over here. And then all you're missing is the 2 that's in front of that. So I can put the 2 there, and then we'll compensate for that by putting a 1/2 on the outside. Now, there is one more thing. So we have our u here, we have our du here. But what is x squared? Well, again, for that, you have to go back to your original substitution. If u equals x squared plus 1, x squared would be equal to u minus 1. And we can plug that in for the x squared. So this integral becomes 1/2. X squared is going to be u minus 1. The square root of x squared plus 1 is just the square root of u. And then 2x dx is du. And this may not look like a huge improvement over your original problem, but it actually is. Because now you can multiply this out. You can distribute here by simply doing the same thing we did in the previous problem. So I'm going to think of the square root of u as u to the 1/2, and then I can distribute this and add the exponents. So this becomes 1/2 integral of u to the 3/2 minus u to the 1/2 times du. So just keep in mind here that what's happening here is I'm thinking of u as u to the 1, and then I'm just adding 1 plus 1/2 is 3/2. And then here we don't have a u, so 1 times u to the 1/2 is u to the 1/2. But now we can take the antiderivative. So the antiderivative of u to the 3/2 is u to the 3/2 plus 1 divided by 3/2 plus 1 minus, same thing here, u to the 1/2 plus 1 divided by 1/2 plus 1. And this is u to the 5/2 divided by 5/2 minus u to the 3/2 divided by 3/2. And then invert and multiply. So 5/2 becomes 2/5. And then 3/2 becomes 2/3. And then look at this. When you multiply by 1/2 here, this 1/2 is going to cancel both of these 2's out. And so you end up getting 1/5 u to the 5/2 minus 1/3 u to the 3/2. And then your final step, of course, is to plug u back in. So let's remember that u was equal to x squared plus 1. So this becomes 1/5 times x squared plus 1 to the 5/2 minus 1/3 times x squared plus 1 to the 3/2 plus c. Next, we have an example involving trigonometric functions. With trigonometric functions, you'll find that sometimes you'll need to be a little bit more creative than you are with other functions. So my first step is going to try to let u be equal to the denominator of the fraction. I mentioned this before. This is very typical. Now, if I do that, we need to calculate what is du. So let's remember that cosine squared of x is the same as cosine of x quantity squared. And when you go to take the derivative of this, you get 2 times cosine of x to the 1 times the derivative of cosine of x, which is negative sine of x. So the derivative is negative 2 cosine times sine, which I'm going to write as sine times cosine. So that's what we have here. But you'll notice that we don't really have that multiplied by the dx here. What we have is sine of 2x. But this is where you need to remember your trig identities. The sine of 2x is equal to 2 times sine of x times cosine of x. This is a double angle identity for your trig functions. So the original integral can be rewritten as the integral of 2 sine x cosine x over 1 plus cosine squared x times dx. And now you can see we have 2 sine x cosine of x times dx. That's all right here. All we're missing now is the negative, which we can very easily put in front here as long as we put one on the outside. And now I can go ahead and make a substitution here. Negative 2 sine x cosine x dx, that's all du. 1 plus cosine squared of x is u. And you know the drill now. This is negative natural log of the absolute value of u, which is negative natural log of 1 plus cosine squared of x, plus our arbitrary constant. Now, one small detail about this answer is perfectly fine, but you actually could remove the absolute value on this, and you could just write it simply as the negative natural log of 1 plus cosine squared without the absolute values. Now, why is that? Well, it's because 1 plus cosine squared is never going to be a negative number, because no matter what cosine is, when you square it, it becomes positive. And when you add that to 1, it stays positive. So the absolute values that you have here, you can remove in this case because this is going to be positive already. But it's not wrong to leave them in your answer either. So now let's talk about what to do with definite integrals and u substitution. So the beginning of the problem is going to be very similar. I'm going to let u equal, in this case, the inside of the radical. Now, let's rewrite this problem a little bit, actually, because if you look at the inside of the radical, you're going to see 1 plus 2x to the second power. But let's think of the cube root of that thing squared. Let's think of that as 1 plus 2x to the 2/3 power. So let me rewrite it like this. Once you do that, it becomes a little bit more apparent that you don't actually want to let u equal 1 plus 2x squared. You just want to let it be equal to 1 plus 2x. So what you want to do with your u substitutions is keep them as simple as possible if you can. So let's let u equal 1 plus 2x. du would be 2 times dx, so everything is good there. Now, I don't have a 2 in front of my dx, so let's go ahead and put a 2. And then, of course, we will put a 1/2 on the outside to cancel that. So now we have 1/2 integral 2 dx is du, and in the bottom we have u to the 2/3. But what about the limits? So remember, the limits here, 0 and 13, those are the original variable x. So when you have a lower limit of 0 here, that's the same as x equals 0. And when you have an upper limit of 13 here, that's the same as x equals 13. What we're going to do is convert both of those into limits involving u. So if x is equal to 0, u is going to be 1 plus 2 times 0. And I'm just getting that from our substitution. So if x is 0, I'm just going to put that 0 right in here. And that's going to give us u equals 1. And then when x equals 13, u is going to be 1 plus 2 times 13, which is 27. Okay? So our new limits are going to be 1 for the lower limit and 27 for the upper limit. Now, once I convert the limits to new values, I don't ever have to go back to my old variable again. So now I'm just going to calculate the antiderivative. Keep in mind, you cannot use the power rule unless your variable is in the numerator. So we need to rewrite u to the 2/3 in the bottom as u to the negative 2/3. And now from here, I can say this is 1/2 times u to the negative 2/3 plus 1 divided by negative 2/3 plus 1. And this is going to be evaluated from 1 to 27. Now, before you start plugging in these numbers, simplify this. So this is 1/2 times u to the 1/3 divided by 1/3. Okay, still not simple enough. This is 1/2 times, when you divide by 1/3, that's like multiplying by 3 over 1. And 1/2 times 3 over 1 is 3/2 u to the 1/3. And again, this goes from 1 to 27. So now I have my 3/2 here. I'm going to plug in 27, so that's going to be times 27 to the 1/3, minus, and then 3/2 again, plug in 1. You get 1 to the 1/3. Now remember, a 1/3 power is the same as a cube root. And so you have 3/2 times the cube root of 27, which is 3, minus 3/2 times the cube root of 1, which is 1. And this is 9 over 2 minus 3 over 2, which is 6 over 2, which is equal to 3. Next example, very similar. Now, we have a pretty interesting function here. We have the square root of 2 plus the square root of x, and then divided by the square root of x. So what should we let u be equal to? Well, you can try anything, because if you're wrong, all you have to do is erase and start over. But I'm going to let u be equal to the inside of the radical, because the square root of 2 plus the square root of x, this is not very nice. So if I let u be this part, at least that will change to be the square root of u. So I'm going to try that first. So let's let u be equal to 2 plus square root of x. Du is going to be the derivative of 2, which is 0, and the derivative of square root of x, which is 1 divided by 2 times the square root of x, dx. Now, if you don't remember where this comes from, remember that the square root of x is the same as x to the 1/2, and the derivative is going to be 1/2 x to the negative 1/2, which turns into 1 over 2 times the square root of x. Okay, so we learned this in Calculus 1. All right, let's go ahead and go through it now. So with this du, are we ready to go? And the answer is not quite. You'll notice that we have a dx over radical x, which is good because we have that right here. But we do not have the 2 down here. So what I'm going to do is I'm going to put a 2 down there, but that's in the denominator. So on the outside, I'm going to put a 2 in the numerator. So I'm going to put like a 2 over 1 there, okay? Because that's going to cancel the 2 that I put in the bottom. So this integral becomes 2 integral 1 to 4 square root 2 plus the square root of x over 2 square root of x dx. And now we're ready to substitute. Dx over 2 radical x, that's going to be du. 2 plus the square root of x, that's going to be u. And so this becomes 2 integral square root of u times du. Look how nicely that's simplified. Now we got to work on these limits. And so if x is equal to 1, we know that u is going to be 2 plus the square root of 1, which is 3. And if x is equal to 4, u is going to be 2 plus the square root of 4, which is 2 plus 2, which is 4. And now we have to take the antiderivative, so let's remember that the square root of u is the same as u to the 1/2. And the antiderivative is going to be u to the 1/2 plus 1 divided by 1/2 plus 1, which is 2u to the 3/2 divided by 3/2, which is 2 times 2/3 times u to the 3/2, which is 4/3 u to the 3/2, and then now I'll bring our limits back into it from 3 to 4. Now, when you have a more complicated expression to work out, you can leave the fraction here factored out. So I can go 4/3, and then I'm just going to plug 4 in minus plug 3 in. Okay, so it looks like this. So we have 4/3 times, now 4 to the 3/2. What is 4 to the 3/2? Well, it is the square root of 4 cubed. And that is 2 cubed, which is 8, minus, and then 3 to the 3/2, that's the square root of 3 cubed. And you'll notice that this is not very nice. So I can rewrite this as the square root of 3 times the square root of 3 times the square root of 3. Square root of 3 times the square root of 3 is 3, radical 3. And then I can multiply by 4/3 to each of these. So I have 4/3 times 8 minus 4/3 times 3 radical 3. Here the 3's cancel, and we end up getting 32 over 3 minus 4 radical 3. And that is about as nice as that answer is going to get. In our next example here, we have the integral from e to the 4th of this interesting function. Once again, when you have a radical, I really recommend trying letting u be equal to the inside of the radical. So let's try u equals natural log of x. Now if we do that, du of course is 1 over x dx. And this is really nice because we have 1 over x right there times dx. And then we have the natural log in here, which is going to be our u. So this is literally just the integral of du over, and then don't forget your square root there. So that's the square root of u. And then we need to change our limits. So when x is equal to e, u is going to be the natural log of e, which is 1. And when x is equal to e to the 4th, u will be the natural log of e to the 4th. And remember, this is just 4 because the natural log of e cancels out. So we just get 4 here. Now to take the antiderivative, first you have to express this as u to the negative 1/2. This is a very important step. And then you can take the antiderivative by using the power rule. So u to the negative 1/2 plus 1 divided by negative 1/2 plus 1 from 1 to 4. And this is u to the 1/2 divided by 1/2. And this is going to be 2u to the 1/2. And this will be 2 times 4 to the 1/2 minus 2 times 1 to the 1/2. And of course, a 1/2 power means square root. So this is 2 times the square root of 4 minus 2 times the square root of 1. And this is 4 minus 2, which is 2. So lots of steps, and it's very important that you do these steps one at a time. And for one final example here, I'll give you a slightly different type of problem. If f is continuous, and let's suppose we know the integral from 0 to 9 of f of x dx is 4, they want us to find the integral from 0 to 3 of x times f of x squared times dx. All right, so how in the world would we be able to find out what this is if we know what this is? So let's start here, and let's think about what do we know about this integral. Well, we don't know very much about it. But we know that if we were trying to integrate it, it would probably be nice to let u be equal to the inside function. And then du, if u is x squared, du would be 2x times dx. And then from there, let's see, what do we have here? Well, we have the integral. If u is x squared, then this becomes f of u. And then we've got the dx here, but du is 2x dx. Notice that we do have an x over here. That's good news. But we're missing the 2. So we'll put the 2 in there, and we'll put the 1/2 on the outside. So this will be a 1/2 out here. And then 2x times dx. We can now replace that directly with du. And then, of course, the limits. If x is equal to 0, u is going to be 0 squared, which is still 0. So I'm referring to the lower limit of 0 here. If x equals 0, you plug it in there. U is going to be also 0. And if x is equal to 3, u is going to be 3 squared, which of course is 9. So we now know that the new upper limit is 9 and the new lower limit is still 0. Now, what about this integral? Well, look here. The integral from 0 to 9 of f of x dx is 4. So that means this integral right here is also 4. These two integrals are exactly the same thing. It doesn't matter what variable you have in here. Okay, if you have the exact same function, it's the same value. So we know that this is equal to 4. So we have a 1/2 out here. That's just going to be 1/2 times 4, which is 2. So just an interesting kind of different problem here, but it still uses the same basic principles of substitution. Now, one final thing to bring up here, I would like for you to think about memorizing the following common integrals. These are integrals that will appear very often in Calculus 2. So I won't bother with reading all of these, but I want to show you why at least one or two of these are what they are. So let's look at the very first one here. The integral of cosine of ax dx is 1 over a times the sine of ax. And if you look at the second one, it's very similar. The integral of sine of ax is negative 1 over a cosine of ax. So why are these true? Well, let's take a look. So if we have the integral of cosine of ax dx, the way to do this is to use a u substitution. So I'm going to let u be equal to a times x. And if I do that, du is going to be a times dx, right? Because the derivative of ax is just a. Well, if you look at your integral, you don't have a times dx. So I'm going to rewrite this now as the integral of cosine of ax times, and then instead of putting dx there, let me put a dx, and then I'll just put a 1 over a on the outside. And of course, the idea here is the 1 over a and the a would cancel out. But now this becomes 1 over a integral of cosine of u du. And we know that the integral of cosine of u is sine of u. But u is ax, and so this becomes 1 over a times the sine of ax. And that is how we prove this first one here. Now, this one works the exact same way. And in fact, this one here also works the exact same way. For all three of these, if you wanted to prove that these were true, they involve the same substitution. You're going to let u be equal to a times x. And I would recommend that you pause this video and maybe try to prove each of these by doing it the same way. For this one here, it's a little bit different. Here you're just going to let u be equal to ax plus b. And then the other ones are actually quite different And I won't do these here in this video because it will make the video longer than it needs to be. But we'll do this in a future video, or perhaps your professor will do this for you in class. And that concludes this video lesson.